Well, in the last lecture, we have talked about all the important properties for the matrix operations, like addition, subtraction, multiplication. So in today's lecture, we're going to get on to the most attracting and mysterious operation, division on a matrix. Okay, let's start. Alrighty, we're finally jump to the step about the division operation of matrices. We have talked about addition, subtraction, multiplication, and we cannot wait to get into the division. And we already mentioned that in the linear algebra, we gave it a special name for the division operation on the matrix, which is called the uh, uh, invert of a matrix. Okay, so let's look at the invertible matrix definition. So here we have, the definition. Okay, so for two matrices, of course, for A and B, now we understand that they must have to be equal on our dimension. Yes, and then we have if A and B's multiplication equals to a special matrix, which is E. Well, E here means the elementary, unit matrix. So equals to something like this. So on the diagonal line of this matrix, we have 1, 1, 1, and on the other positions, we only have 0. So okay, so now we can say that A, B are invertible. Okay, and then we can have, BA equals to E for sure. So this time you can see that although in most cases we cannot say, for any arbitrary matrices A and B, we have the commutable law to be true. Usually that's not the case. However, for this invertible matrices, okay, now we can say that A and B's multiplication, no matter which one is on the left, which one is on the right, will always be this E matrix. And also we can say that the A's inverse matrix will be B. And also the B's inverse matrix will be A. Okay? So in this case we have A times B equals to B times A. Okay? Alrighty, so that's the definition about the invertible matrix. Yes, that's the definition. And in the following, we're going to talk about the properties about this division operation. Just like, we talked about the properties about the other like multiplication, subtraction properties in our last lecture. So let's look at the properties. Okay, so the first one is about this. So we have inverse matrix of A, and we do another inverse operation. So what's going to happen? Yes, that's very easy. You can see that it will become A again. So in our definition, we're going to do a very simple explanation here. So the inverse matrix of A will become B. Okay, so if we do, the B inverse, we'll have A. So that's why we have this as A. Yeah. So that's the logic here. All right. So the next property of the matrix will be so if K as a constant is a non-zero constant. So we have k times a, we have inverse here, will become, well, in this case, some students may got very confused. So let's look at, get back to the definition of the invertible matrix. So, we say A and B's multiplication equals to E matrix. So that's why we can say, oh, A's inverse will be B, B's inverse will be A. The same thing. So let's look, take this whole thing. K times original matrix A as a new matrix as a whole, right? So this time, all we need is trying to find a special matrix which can make this multiplication to be E matrix. Well, you have to think about it. So my answer will be, this. As you can see that when this constant times this constant, because they are not matrix, but the constants. So they obey, the commutable law in the regular algebra. So this one will be cancelled out. And, A times A inverse will also be E. So this time we'll get E for sure. And now you can say that, well, the K times of matrix A's inverse will be nothing but the 1 over K, okay, 1 over K, well, times A is inverse. Okay, so that's the second property. Let's look at the third one. So if we have a multiplication of matrix A and matrix B, and we want to find out the inverse of this whole thing, what would it be? Well, in the second properties proof, we understand that if we want to find out something which we're not familiar with, we just have to refer to the definition of the invertible matrix. Yeah, so here, let's do it again. So A, B as a whole matrix, right? So we have to let it times another matrix equals to this E matrix. Okay, so this time think about it. Although we don't have the mutable law universally for the matrix algebra, but we do have the associated law. So it means if we put a B inverse here and A inverse here, let's see what will happen. The B times the B inverse will become E, and A times the A inverse will become E again. So this time we will have E. So we're going to put it here as B inverse and A inverse. Well, and here you can see that we change the order. We have A on the left, but we have a B inverse on the left here. So, myself, this is like something which can help you to remember. This is like, the where, what do you say, put on, and take off. Take off rule. It means, well, you put on A first. For example, A is like your underwear, so you put on A first, and B is as your coat, so you put on B later. But then you have to take off B first, and then take off A later. Or in computer science, this is more like a stack algorithm. Okay, so we're gonna talk about this one. Gonna use it later a lot. This one is very easy for you to remember intuitively, and also very useful for us to solve the complex problems. Alrighty, so the next one is about the matrix transpose of the matrix A itself. So in some cases, we have to transpose the matrix A, but then we have to find out its inverse. So what would happen? Well, this one is actually very easy too. Now you can see that. So we want to find out a matrix which times this A transpose equals to the E matrix. So let's do something here. So we have a matrix also with a transpose here, but we have, the A inverse here. Okay, so this time we can have this guy and this guy times first, and then do the transpose. And of course, the E transpose will also become E. So that's why we can just put it here as A inverse transpose. Yeah, this is also very intuitive. Okay, so the next one is going to be kind of, sorry, this should be 4 and this should be 5. Very interesting. So I'm trying to, set up the bridge between the matrix and the determinant again. So this time we have the A inverse like this. So we put a determinant sign here. So what would it become? Well, is there any relationship between, this guy and the determinant of original matrix A? Well, let's look at this. So for example, so if we have this A and B, okay? So AB, we understand that A is the inverse of B, B is the inverse of A. So when they multiply together, they're going to give us E, of course. Okay? And we understand that, from the last multiplication property about the determinants, so A and B's products determinant is nothing but, their determinant product, like this. Okay? And we understand that the determinant of, E matrix will become E, 1. Okay? So this time, let's, do some transformation for A and B, because they are the mutual inverse matrix to each other. So we can say it like this. Okay, so that's why we can conclude, well, the A's inverse matrix's determinant will be 1 over the determinant of matrix A. Alrighty, so we can just put a 1 here. Okay, so that's the proof procedure of this guy.